Imagine a single beam of light, so precise it can cut through steel, carry your voice across the planet, or even reshape your eye. It's called a laser. You've seen them in sci-fi weapons, barcode scanners, even your dentist's office. But here's the thing. Do you actually know how a laser works? Most people don't. And yet, lasers are everywhere, from your phone's camera to fiber optic internet, eye surgeries, space communication, missile defense systems, 3D scanners, autonomous vehicles, and even quantum computing. What started as a physics experiment in the mid-20th century is now one of the most transformative technologies of the modern world. So how do they actually work? What makes laser light different from a flashlight or the sun? And why are lasers suddenly the backbone of everything from medicine to military tech? This is the full story of light, atoms, mirrors, and the science that turned them into one of humanity's most powerful tools. The word laser is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. That sounds complicated, but at its core, a laser is a beam of light that is very pure, very focused, and very powerful. Unlike the regular light from a light bulb, which spreads in all directions, is made up of many colors, and is relatively weak, a laser beam is monochromatic, one color or wavelength, coherent, the waves are in sync, directional, it travels in a tight, narrow beam, and intense, all energy focused into one precise line. But how do we create light like this? It starts at the atomic level. To understand lasers, we need to look at how atoms work. Atoms have electrons that orbit the nucleus in specific energy levels. When you give an atom energy, like from electricity or a flash of light, an electron can jump up to a higher level. But that's not stable, and the electron wants to fall back down. When it does, it releases energy in the form of a photon, or a particle of light. This is called spontaneous emission. A photon comes out at a random direction and phase. But something weird and powerful happens if a photon of the same energy passes by an excited atom. That atom will release another identical photon in the same direction with the same phase and wavelength. This is stimulated emission, the key to lasers. If you surround a bunch of atoms in a special chamber with mirrors and excite them, they start bouncing photons back and forth. Each photon stimulates more atoms to emit more identical photons. And just like that, you've got a chain reaction of light. That's how you amplify light. That's how a laser is born. So what do you need to make a working laser? There are three main parts. 1. Gain medium. This is the material where stimulated emission happens. It could be a gas, like helium neon, a crystal, like ruby, or even a semiconductor, like in your laser pointer. 2. Energy source. Called the pump, this gives energy to the atoms in the gain medium. It could be electricity, a flash lamp, or even another laser. 3. Optical cavity. Two mirrors on either end of the gain medium. One is fully reflective and the other is partially reflective. The photons bounce between them, triggering more emission until the beam escapes from one side as a tight, intense laser. All of that to get one perfect beam of light. The first working laser was built in 1960 by Theodore Maiman using a ruby crystal. At the time, no one really knew what it was for. It was a scientific novelty. Maiman himself joked that lasers were a solution looking for a problem. But it didn't take long for people to find uses. In the 1960s and 70s, lasers began appearing in rangefinders and targeting systems for the military, high-precision tools in manufacturing, medical treatments for eyes and skin, optical research in physics and chemistry. And then, one day, something incredible happened. We figured out how to use lasers to carry information. Have you ever wondered how information travels across the world in milliseconds? Lasers made it possible. Fiber optic cables use tiny pulses of laser light to send data, at the speed of light, across continents and oceans. These cables connect the internet, phone networks, and even your Netflix stream. Each pulse of light can carry a 1 or a 0 digital information. And because laser light is coherent and directional, it can travel long distances without losing strength. This single application revolutionized communication. Lasers are also used in CDs, DVDs, Blu-rays. Lasers read and write microscopic dots of data. Barcode scanners in every grocery store checkout line. Laser printers using static charge and toner. LiDAR systems helping autonomous vehicles see the world. Quantum communication for super secure data transfer. Lasers have become essential in modern medicine. Laser eye surgery reshapes your cornea with extreme precision. Laser scalpel tools can cut tissue with minimal bleeding. Laser therapy is used for tumors, skin resurfacing, and dental procedures. In manufacturing, lasers are used to cut metal with ultra-fine precision, weld complex joints in car bodies or electronics, etch microscopic designs into microchips. Industrial lasers are used in range-finding, targeting, and directed energy weapons. Weapons that destroy objects using focused energy with no projectile. This is not science fiction. Militaries are already testing laser turrets on aircraft and ships that can burn through drones, missiles, or small boats in seconds. Lasers are also at the heart of major scientific breakthroughs. Gravitational wave detection with LIGO uses laser interferometry to detect ripples in space-time. Laser cooling slows atoms to near absolute zero, used in quantum computing. Femtosecond lasers can create pulses so short they can film chemical reactions at the atomic level. Nuclear fusion experiments use lasers to compress and ignite fuel, mimicking the sun. And in the near future, lasers may be used for space propulsion, using laser beams to push light sails across interstellar distances. Laser-based internet from space, like what Starlink is exploring. Biolasers, using living cells as gain mediums for health monitoring or diagnostics. Lasers used to be rare, expensive, and fragile. Today, because of advances in semiconductors, micro-optics, and manufacturing, they are cheap and scalable. That's why you can find lasers in your phone's facial recognition system, your smartwatch's health sensors, factory automation robots, smart home devices, your car's parking sensor, your dentist's office, your internet router, your entertainment systems. The laser has gone from lab curiosity to an invisible backbone of modern life. So the next time you scan a QR code, stream a video, or get laser eye surgery, remember, you're not just using a beam of light. You're using one of the most precise, powerful, and revolutionary inventions in human history. Lasers aren't science fiction. They're science fact, quietly shaping our world, one photon at a time. If you found this deep dive into the world of lasers fascinating, make sure to like the video, subscribe for more eye-opening tech and science stories, and leave a comment telling us the one laser use that surprised you the most. Thanks for watching, and as always, stay curious.